Okay, so thus far we have looked at gravitational potential energy, Vg, and we've looked at elastic potential energy, right? And that was Wy. And what we saw is that this was simply the potential energy at a certain point, and it's based on its position, right? So for each of these we have to define a datum. For the gravitational potential energy, you just define a datum. Anything above that line, we have positive potential energy. Anything below that line, we have negative potential energy. For the spring, the datum really is the equilibrium point. What is equilibrium? It's the point where the spring is not stretched or compressed. And anyways, the potential energy in a spring is always positive. If you compress it, it's positive. If you stretch it, it's positive. Whereas the potential energy due to gravity is dependent on the datum. Above it is positive, below it is negative. So we'd like to introduce something called the potential function, which includes now both of these. So V is now equal to the potential energy due to gravity plus the potential energy due to a spring. Okay? If your problem involves both gravity or weight as well as a spring, then we can include this as our potential energy function. Okay? And what we'll see, I don't want to derive it here, but the work done from 1 to 2 by these conservative forces, weight and the spring force, is equal to the potential energy of the spring and gravity at state 1 minus the potential energy at state 2. Okay, so here is an example. So say now we have a spring, vertically it's hanging, and then we have a mass as well. Okay, so what do we have here? We've got both spring force and we've got weight. Both of these are conservative forces, okay? And we are trying to determine the work done from 1 to 2. Okay, so this is going to help us, obviously. So, what is basically we're looking now for the potential function at each state, at state 1, at state 2. So, say now at state 1, okay, we've got V1. So we define our datum. Remember that if the mass piece is below that datum, we are going to have negative potential energy due to weight, due to gravity. So we are going to have minus the weight times S, right? Remember that the potential energy due to gravity is W times Y. If it's below the datum, it's negative. Okay, and Y is just how far it is below the datum. So we have minus Ws. And the potential energy in the spring is positive. It is half Ks squared. So the total potential energy in the system at the moment is the negative potential energy due to gravity and the positive potential energy stored in the spring. Okay? So that S just means that the spring was at equilibrium, and then we put that mass piece on and it moved down to there. So it moved S. Okay. So let's just make that V rather. Okay. So say now then it's that's V1, which means that would be S1 and S1. V2, say now this spring is stretched even further down to S2. Say it's stretched even further down, so that was S1, and that goes down to S2. Then V2 again, because this mass is below the datum, it will again be negative, but it'll be minus WS2, and the energy stored in the spring would be half Ks2 squared. Okay? So then we know that the work done from 1 to 2 is V1 minus V2. So we're going to take that V1 minus V2, and we're going to have this. All right? So this is eventually what we have. Okay. So this is just a small exercise to show how we work with potential energies, potential function.